Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
This is Chris Jackson. We were talking about systems engineering and how that relates with reliability engineering, or maybe more correctly, in some instances, doesn't relate with reliability engineering.
I don't know. I've run into a handful of people in systems engineering, and I'm like, oh, what's that? And I'm like, I don't think I quite get it. We look at the big picture, and it kind of made me think of the guy sitting on the beach, you know, meditating with the sun or something. I'm like, well, what is it you do? And, I'm being a little bit facetious. And I also know that in some systems, you can get a really good hard drive, you can get a really good motherboard, but they won't talk to each other unless somebody actually thinks about how are they going to talk to each other. And I think that could be a sliver of what systems engineering is about. But I don't know. I've never really dove into that field or area, except to find out one time that they thought that they invented reliability engineering. And I'm like, well, wait a second. But that might be just me.
Well, systems engineering it's a really, obviously a very useful and important discipline. But I just think, like with any discipline, including reliability engineering, it can be used to help, or it can be used to hinder and feather the nest of egos and things like that by feeling good by getting involved in the process of actually adding any value to the process. I don't know. Is that your experience, Fred?
Well, yeah, and it's true. There's lots of different groups that do that. And I was talking to Diana the other day about quality engineering and quality departments. And sometimes they actually add a lot of value. They actually come in and ask the right questions. They bring in the right tools at the right time and foster the creation of a decent product that meets customers' expectations. And other times they're the stereotypical lab coat clipboard at the end of the line going, nope. And I'm like, come on, actually do something useful. And the systems engineering part, it's great. Somebody's looking at the big picture, but some point you actually have to call the vendor and see if they're going to ship us the parts. You can't, it's not simply just go, we get it from the vendors and wave your hand. It doesn't happen then.
I think my biggest issue with systems engineering when it's applied incorrectly is the systems engineering V model, where you go from left to right. You start at the system level, then you move down to the subsystem level, and then component level. What I mean by that is, you work out your requirements, your specifications, and your functional performance specifications, and all those things. Mm-hmm. And then at the system level, and then you break them down to subsystem requirements, specifications, and goals and targets. And then once you've done that, you break them down into component goals and requirements and specifications and so on and so forth. Mm-hmm. And then you get to the creative act of designing or creating components, and they get, in the V model at least, they're supposed to be put back together to create a subsystem which you test and validate. And then you get the subsystems and you put them together and you test to validate the system. So you go down through the requirements, design the components, and go up. And the premise is that if you follow this process, your system is all but guaranteed to be awesome.
Right. I've never seen that work.
No, there's many problems with that. Most of us know that design is iterative, and most of us know that you will inevitably come across some challenges in the design space that you weren't anticipating. And if you have an issue with your power supply, which is one subsystem, you might have scope to be able to address that issue with power supply with the electronics team who are able to, I don't know, put filters within their circuit board, so on and so forth. Mm-hmm. But the V structure, the V model, where you go requirement, design component, put back together, test, put back together, test some more. And if you follow that process, it's all good. Doesn't allow for that sort of iterative trade-off, let's go back and revisit this, which is an important part of making awesome things.
Well, I think, and in this one, I'm speaking out of my field of depth, but agile approach to, is kind of the other end of the V spectrum. It's like, let's really focus on this for 2 weeks and try to get these two things done. And it's at component and it's at every level simultaneously. Let's just focus on it. Let's get a prototype together and let's get a model together. Let's get something put together and try it. And I imagine it could be forced into a V model, but setting the specifications without understanding what's feasible, what are the trade-offs, what are the hurdles, and expecting, well, if we set the specification that we're going to do this Bluetooth, but it has to have a reach of 2,000 meters, well, it's not technically possible. And just assuming you're going to get an invention that's going to solve that is a lot of folly. And that might be what you want, but there's a lot of crossover. I think what's missing from the V model is the loops. As we learn things, we go back and look at the requirements again.
Right. And systems engineers who are listening to this podcast might be shouting with rage, and they say, well, the V model it's not, you're not supposed to follow it religiously. It is a guide, and I do like the concept of hierarchy and structure, and your components need to come together to create subsystems, which then in turn need to come together to create systems. Mm-hmm. Problem is, we have systems engineering courses where you'll have people with no background in design, no background in mechanical engineering or electrical engineering or software engineering. They get this systems engineering course and they know nothing else. There's this almost religious fervor that if you go through processes like the V model, you will get the desired end state. And if you don't, then someone stuffed up. Someone made an error, and that person needs to be burned at the stake. That's the
and I've given you a hard time for being a well-educated reliability engineer. Yet I also know that you've got a lot of practical experience in engineering. So it's the ones I have hard time with is in reliability. Go through school, have never been in a factory, have never been on a design team, and come in as a newly minted PhD reliability engineer and have the same phenomena. They say, well, if we do the Weibull plot, if we do this, we do that, it's all good. And then they just fall flat on their face unless they can figure out how to talk to engineers, to design teams and management teams and everybody else. And and I think systems engineering, the way you just described it, is one of the problems. If a really good program manager, somebody that's been an engineer, a designer, and gets elevated because he or she's got great coordinating skills and people skills and soft skills. I heard it phrased the other day, it should be not called soft skills, it should be called power skills. I thought that was clever. And then they get elevated to somebody that coordinates the team, the various groups of engineers to design something. Then getting a lesson, a course or education in systems engineering would be like adding an MBA to somebody's credentials if they already know how the ins and outs of how their business works. Now they could look at what's the theory say and have something to compare it against. I think that's where those frictions come in.
Yeah, and to be fair, it's not just systems engineering, it's not reliability engineering, it's every engineering where you have bright young things who, some of them just get straight out of high school, go straight into uni, get their undergraduate degree, then without ever leaving uni, become postgraduate student and get a job at the university to help drive down fees, and then they, with their aim to get a PhD, and by the time they're 28, they have a PhD, which is normally the highest sort of qualification you can have. Mm-hmm. But they've spent those brutally important formative years in their early to mid-20s never having to talk to people or never having to walk the factory line or never having to motivate people. It's just very assignment-centric, very statistical analysis-centric.
There's an answer at the end of the day.
Yep. And as you and I both know, universities by definition, when you do postgraduate study, you're supposed to research something that adds to the state of the art. That's the fundamental term. But in practice, it means You need to research something that no one else has researched. Problem with reliability engineering and systems engineering is it's been around for a while. There's not a lot left to research. The stuff that's left to research is stuff which tends to be less and less relevant, as you and I both know. So it's a problem.
Let's consider adding a half column to the next FMEA, and we'll consider that a marginal improvement to nothing. And then here's the evidence, and in theory, and blah blah blah. And I'm like, okay, whatever.
Right, and that's not. You sound facetious, but you're actually citing
some real
world
research
examples. Yeah. Another example is where we have materials labs which try to find ever increasingly more sophisticated equations that model physics of failure, which go from 10 parameters to 27 parameters, which have a definite improvement in how well you can predict times of failure. But because it's physics of failure, you need to input relative humidity, temperature, cycle of the moon, the star sign of the person using the device,
the grain structure of the ceramic,
Yeah, absolutely everything. And it becomes beyond practically feasible in the real world. And what you want is actually someone to realize there's a problem with fatigue here. Let's just shot peen that weld. That is a 5-minute call that will circumvent what those, I suppose, university qualified reliability engineers would prefer to do, which is have a 2-year study, which they can publish 3 papers for and add it to their Google Scholar bibliography. I'm being facetious, but not really.
We've met plenty of them. But back to the systems engineering. I vaguely recall looking into some of this stuff, and what is systems engineering, and it came about kind of I think in the Second World War, and the big military projects, big submarine projects, big aircraft carrier projects, great big dam, like the Hoover Dam projects, things like that. There were so many moving parts and such a timeline to get it all done, and so many different disciplines involved, that it wasn't like hiring an architect that was going to design a building that already knows the ins and outs of the plumbing and electrical and the structural and aesthetics and everything else. Is that there wasn't any one person that could see the whole thing and make it all work, and knew enough to not trip over it. And so the systems engineering kind of concept, correct me if I'm wrong, it came about as a methodology to organize these very large, complex projects. And I don't see it in most product development teams where there's, even up to 50 engineers. There's some systems engineering tools being used, but there isn't a systems engineering person or department, by and large. That's just been my experience. So I haven't really run into it too often, but I have seen some of the tools. I have seen the V model that gets used lots of different places. The concept of setting specifications and then, going after the smaller parts and looking at the interfaces and having a block diagram at higher levels and concept phases. Those all make sense. Yet hiring a system engineer for a 4-person team just doesn't seem to make. It's like hiring a reliability engineer for a 4-person team. It's like, well, they'll have about an hour of work to do, that's about it.
Well, and I think I am not as familiar with the history of systems engineering to challenge how you described how it came about in too much detail, but my understanding of it too was more during World War II, when new wartime technologies are becoming more and more relevant, they realized they need to do something more than project management. So systems engineering was the next step beyond project management, where everyone knows what they need to do in a way. And yes, you have goals and Gantt charts, but the idea is that systems engineering, you have these different moving parts with different outputs that need to interface with each other in ways that never had to before.
Yep.
And I think one of the challenges with today's systems engineering is that it's often aligned to contractual relationships between big bureaucratic customers, governments and militaries, and industry providers. When it's built into the contract, you do this test and validate and verify, and then blah 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 blah.
And it ignores that it's an evolving process, that was my last run across the systems engineers was, well, it's a large complex system and you don't understand it. We have the big picture here, and it was pretty much what they said. And we're going to simplify it all. That's why we use MTBF. And I'm like, okay, this isn't going to work.
Nope.
And it was just. The idea is to recognize that it is a complex system. I thought that was the point. And it's not to smooth it all over of the areas you just don't want to talk about or understand and call it good. Well, that's a pretty good recipe for disaster. I saw a great example of this yesterday. I'm recording a course on, and the speaker, she was using if you only can take 2 points of data and you take them really far apart across, say, the temperature range that the system can operate. And in the low end, and she used a cooking example or an analogy, says if you bake cookies and you want to know what's the right temperature, what's the best temperature to cook these things at, such that you can see a difference between good and not so good, that it's far enough apart in temperature that you can detect a difference. And so the theory is, well, if you put it really far apart, that's better, right? And she says, well, if you bake cookies at 25 degrees, they'll just remain raw. And if you cook them at 500 degrees, you got ash, right? And she also said that if the relationship is not linear and you only have those 2 points, you draw a point across those things, and the further apart they are, the bigger the difference is if it's not linear. If the relationship of what you're trying to measure or output is. And so if you put those closer together, that single line is still not right, but it's closer.
Right.
Right. And so part of looking at big systems, and I think the talk about the physics of failure guys are kind of going the opposite direction. We're going to put data points in relationships everywhere. Mm-hmm. To the point where we just can't possibly get enough information to populate it and get anything useful out of it. So we end up simplifying it, going, well, it's ceramic. How different are they really? Let's just put in a 2 in that value. To the other extreme is that you buy in the model itself. Well, let's pick 25 and 500, and we know it's in the middle there someplace. So it's close enough. And no, you're setting yourself up to just be wrong,
right,
all the time. And I think a good systems engineering team or person will understand that things are not linear. Things are not. Things have interactions. Things are learned along the way of designing a system or a process that involve changing things, and that's including the requirements. That's okay, but when you write massive contracts 15 years before you start working on it, and that's the goal, that you don't get money unless you do it exactly according to this, super simplified process from 15 years ago, then I don't know. That's been my experience when I run into military systems that are under this process. It's like, don't wonder we can't get anything that works.
Well, the MTBF, I mean, I've come across that systems engineer multiple times where I haven't had that exact scenario, but they want to say, look, you puny little reliability engineers, you don't get the
big
you don't
picture.
Yeah, I am just 3 steps below God. You are but a small cog. And the reason why we need MTBF is because that is big picture thinking. Now, you can faff around and keep talking about little reliability at, reliability of 90% at 500 hours as much as possible, but unless you're talking big picture language, you're not relevant. So come back to me once you've answered that problem. The problem with that is, you and I both know, is that we can create any statistical model where the MTBF is a little bit over 500 hours, or all the way out to, for all intents and purposes, infinity, where we satisfy the requirement of the reliability being at least 90% at 500 hours.
Yep.
There's no answer to that question. And that's one of the many reasons that systems engineers, the sort of very theoretical application of systems engineering, results in substandard equipment because the customer, the soldier, the ambulance driver, they need this thing to have a reliability of 90% at 500 hours. But the systems engineer who has done a postgraduate degree after they got their geography undergraduate 10 years ago, no, they know what they're talking about. It's all down to MTBF because that's big picture thinking.
Yeah.
The reality is they haven't been taught what these actual metrics mean. They're so focused on the process because that's the only thing they have. They don't have the design background. They don't understand the mechanics. And it's frustrating. Now, I'm talking about a subset of systems engineers. I shouldn't say they're all like that.
Yeah. And the one or two of you that are systems engineers that listen to this, you know, yeah, we'd like to hear from you. What's your take absolutely. On this? Give us an education here. What's up? What are we missing? You know, but, yeah. And I think we could also pick a handful, like we mentioned a couple of times, a handful of other disciplines. There's a bit of practicality to it.
Reliability engineering is perhaps the biggest one. I think it's a perfect case study of how a discipline can sometimes be taken over by impractical theory.
Oh, let's do nothing but models, or better yet, let's do nothing but exceedingly long characterization, accelerated testing things. You know, that'll take 5 years before it can tell you vendor A is better than vendor B.
Right.
And nobody really cares. So
the other thing about systems engineering is it doesn't place any emphasis on building relationships with suppliers. There's none of that. You and I both know the organizations that do the best, who are the biggest suppliers of stuff across the world, tend to be high quality organizations. Toyota, for example. Yep. We know plenty of others, but Toyota is one of the few that have sort of published the way they do things. But they invest in their suppliers. The systems engineering doesn't relate very well to how they create vehicles which are clearly more reliable than pretty much any other vehicle on the road. And by the way, they happen to be the world's largest automobile manufacturer. Funny how they it sort of interacts with each other.
Well, it does, and you know it also improves reliability when you have a good relationship with your vendors, because you can actually understand where the problems are and the potential failure modes are, and solve them well before you get to meeting the contract, which may or may not be useful. And I think that's part of it. I don't know if it's just systems engineering that writes these contracts, but there's plenty of them. That's where I've seen it really shine as a dull lump of coal. It just doesn't kind of work.
You know that systems engineering has gone mad when the suppliers have to employ systems engineers who do nothing else but interact with you, the customer, in your systems engineering gobbledygook. If they have to pay salaries to people whose only job is to interact with your systems engineering language, that means you have lost focus on things like good design, high quality manufacture, user interaction, all those good things. That's one of the biggest symptoms of the world gone mad for me.
Okay. Well, let's give our one or two, if they're still with us, systems engineering guys a chance folks to give us a shout.
There are good ones out there as well. We know that. There's terrible reliability engineers out there. We know that too. So we're just talking about the pitfalls of those people who don't get what we're here to do.
Yeah, maybe we should recall this, but it'll get to some attention, I think. And there is overlap when it works well. We can work together. We have common objectives. We can get things done. We make a good product and experience for the customer, and everybody's happy.
100%.
And that's all good. So, all right. So, yeah, if you're listening to this and you're going, wait a minute, these guys are great, or this team's good, this made their difference, let us know. Or if you got a question of how do I deal with these folks, that might make another good episode there. In any realm, whether it's system engineering or anywhere else, if they're the ivory tower, here to save the organization, well, what do you do? And it might actually be useful, heaven forbid. But the idea is that, how do you respond to this stuff? What do you think? You can let us know. You can join the conversation over at accendoreliability.com/go/SOR. You can leave a short rant up to 90 seconds on on our recording widget there, or you can leave us a longer comment if you'd like. You can Chris and I and the other hosts of the show are available through LinkedIn or our About pages. There's plenty of ways you can get in touch with us. And we certainly listen and use the comments and questions that we receive and ideas that we get recommended to us for episodes. And if you've been listening to more than a few episodes, you know that's true. And we also try to get you an answer back to, if it's a question, we try to get you an answer back directly, and then we'll evolve it into a show at some point. So please do look forward to hearing from you. And so with that, Chris, I'm going to avoid all my system engineering friends for the day that this podcast comes out.
Fair enough, Fred.
We'll talk to you soon.
Cheers, Fred.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.